Good morning, everyone. My name's Katie Yacht, and I'm with Watershed Science and Design out of Boulder. And thank you guys for accommodating me on video. My vacation planning greatly appreciates it. So yes, we're going to talk about the Sand Creek, Coal Creek Fluvial Hazard Zone mapping that I did along with Round River Design, Michael Blazowitz out of Salida, Colorado, and Joel Schultes, who's out of Grand Junction. Sponsored by the Mile High Flood District and Morgan Lynch, which has been a great partner for this pilot project. When I was putting together this presentation, I was thinking it was more of a 201, a little bit more in depth and a little bit more on applications and how to interpret maps versus a kind of, entry-level 101 presentation on what fluvial hazard zone maps are and how they're created in the different types of them. So if there are any questions kind of on that more foundational stuff, I know that you guys have heard about it before, but if there's more questions on that, I'm happy to answer that in the Q&A session. And, always feel free to just give me a call or shoot me an email and we can talk about that at any point that a question may come up. So with that, let's get started. Whenever I do a fluvial hazard zone presentation, I kind of like to start with the bottom line up front. So what are, what are our base assumptions? What does fluvial hazard zone mapping actually get you? And these are the 5 tenets that we've got today. So number 1, streams are dynamic, they move, and because they move and they have energy, they require space in the landscape for them to expend that energy and to store their sediment and their water. Foundationally, this concept is that streams are corridors and not lines. When I give presentations to bigger audiences, I always like to say, if I could change one thing about the way we talk about rivers and streams, is that I would take every road map and I would transfer every little squiggly line into a corridor, just so our base understanding as a society is that streams are corridor, not these squiggly little things that exist in a tiny little discrete point in space. I also want to be clear that the fluvial hazard zone is a way to define the space that streams occupy and influence. It is not the only way, but it is a way that was developed in order to help users understand the hazards that are associated with stream movement and sediment movement through a corridor. There are definitely other ways of defining that space, depending on what the objectives are. If they're, if it's a functional floodplain and we're looking at it for ecologic purposes, there's other ways to quantify that. But today, the fluvial hazard zone that we're talking about is really focused on spatially defining the hazards that come out of a stream corridor. This space, as I mentioned before, can be used for better or for worse. It is a place where there is substantial hazard, and as such, it's may not always be a good idea to put investment into that area, but that space can also function as flood wave attenuation, sediment attenuation, and really start to work as green infrastructure in our cities and in our communities. And so there's actually a lot of benefit that can come from recognizing this space as well. And then I'm going to give you a few examples of how fluvial hazard zone maps can be used and how to interpret them. So foundationally, what we're looking at is instances like this, where a river breaks out of its channel, moves sediment, moves energy, and ends up in locations that it maybe wasn't before. And sometimes these locations are historic locations, as in this is where the channel was 50 years ago, 70 years ago. And sometimes, depending on the system, and potentially a system like Sand Creek, it could end up in a completely new location. So just looking at historic alignments isn't, the full picture when we're thinking about dynamic channel movement in some systems. This is a picture of Cherry Creek in 1864. This is, stream movement. Erosion is not a new problem. We've been dealing with this for a long time. And foundationally, what this program tries to do, or what fluvial hazard zone mapping tries to do, is provide the framework to predict what these responses are, because ultimately, once you understand conceptually the science and the physics of these systems, it's easier to understand that the flood responses are predictable, and you can start to look at a landscape and understand how a river is going to change over time when it gets a big flush of energy or a big flush of sediment, either from a rainstorm or in off cases, big snowmelt events, or in some watersheds if there is a big wildfire. So we're looking at this as well, it's true. We're looking at this because river response is predictable, and there's now a framework to understand how to put delineations on the ground that capture those types of responses. So what is the fluvial hazard zone? The fluvial hazard zone is the area a stream has occupied in recent history. So again, that past component may occupy the future component, or may physically influence as it stores sediment, water, and debris during a flood event. Sometimes these responses in river corridors happen kind of instantaneously during a flood event, or sometimes they can happen incrementally over time. And this is a way to look at both of those processes, either in a very short term or kind of over a long-term framework. As I mentioned, we can also look at these hazard zones as blue-green infrastructure, as connected floodplains, and as assets to our community and part of our flood mitigation and control systems. I'm going to just leave that there, and we can talk about that more as, if we want to talk about that during the question session. But just know that, again, these areas are not just, hazardous no-go locations. They really can be fantastic community assets and work really, really well to protect downstream and adjacent communities and developments if they are protected or conserved and in a physical configuration that allows them to store water, sediment, and dissipate energy. So how are fluvial hazard zone maps different from floodplain maps? Fluvial hazard zones can be either bigger or smaller than a traditional, FEMA floodplain map. It just depends on the type of system we're working with. In Sand Creek, the fluvial hazard zone is bigger than the inundation zone or the FEMA floodplains, which is, probably why it was chosen to be a pilot project for this program, or with the City of Aurora. So what it's looking at is it's looking at that area of movement on the stream bed, or on the bottom of the stream corridor. And for the most part in Sand Creek, that matches really well with the FEMA 100-year floodplain. But it's also accounting for the fact that that river can move, or the Sand Creek can move into the bluffs and into the sandy terraces and begin to tear those down in a flood event as well. And that's the hazard that's missed in the FEMA floodplain mapping for streams like Sand Creek. It's that erosion from underneath that causes collapse of terracing and valleys. Other systems are different, but for Sand Creek, that's generally the hazard that's going to be existing outside the 100-year floodplain. So how do we do this? So floodplain maps, we're all pretty familiar with those. It's basic hydraulics and hydrology. It's all kind of physics-based or empirical. But the main issue is that even within the 100-year floodplain, not even counting the bluff or the terrace failures, hydraulic mapping or hydraulic modeling assumes that the channel bed is static and that the landscape isn't changing underneath the model. And we also just know that that's not a true assumption in dynamic systems in areas like Colorado, where we have we can potentially have very steep systems with big sediment loads. And so what we've got here on the right is the hillshade of a section of St. Vrain Creek before and after the 2013 floods. And we can see that there's areas of that landscape that changed by over a meter. Some of that change is actually on the order of 2 meters. And so if you're dealing with erosion and it's down cutting, that's one issue. But the other issue is when you have deposition of that sediment and that valley floor or that channel bed is raising by a meter or 2 meters in some instances, that means that your inundation mapping is dramatically underestimating the extent of flooding, because the channel effectively no longer exists in a lot of these locations. So just something to keep in mind when you look at floodplain mapping, just understand that the ground surface underneath the water is not changing in standard modeling, and depending on the system, that can really start to break things down. And this is something that fluvial hazard zone mapping accounts for. And, as such, it gives a little bit better idea of the susceptibility and the hazard in some areas, depending on the system. So how exactly do we do fluvial hazard zone mapping? I'm going to conceptually kind of go through the tenets of what we talk about, and then how that applies to what you may be doing and using it to make decisions and review plans and such. So the first thing that I look at when I do fluvial hazard zone mapping is sediment continuity, and that is effectively just where is sediment entering the system, where is it being deposited, and where is it exiting the system. And that gives us a good idea of, again, those hazards kind of associated with deposition and change of that floodplain, like we saw in that St. Vrain example. So are we a net holder of sediment? Is sediment coming in from hill slopes and upstream reaches, and we're just basically going to stop it in our reach, causing that aggradation or causing that increase in floodplain and channel elevation? Or is this a net export of sediment? Are we just eroding channel banks, and then because the energy is so high, are we just flushing it out to downstream areas? Similarly, I also look at energy dissipation and flow storage within the system, within the reach, and within the floodplain in the same way. So you can think about floods as basically balls of energy as well. So there's this ball of energy that's in the water and in the debris that's coming down. And when it hits your reach of interest, is that energy going to be dissipated, or is it going to be transferred? And oftentimes when we do civil works projects, to transfer this energy to downstream reaches. And if the reach downstream is able to handle that because it's a natural floodplain, or has a lot of space to change and deposit sediment and erode banks, that's not an issue. But sometimes when we look at, but oftentimes when we're looking at civil works or, riprap projects, all we're doing is transferring energy out of the reach, which effectively is just transferring the problem. And so that's another thing that I look at when we do fluvial hazard zone mapping, is when this energy comes into our reach of interest, is it being dissipated? And if it is it being dissipated in a safe way or an unsafe way, or is it being transferred to the next reach or area downstream? And if it's transferred, what does that mean to that reach? Is that increasing the hazard down there, or is it an area that can take that energy and safely dissipate it before the water and sediment then move downstream? And one of the ways that we look at this quantitatively is through the lens of unit stream power. And the most important thing to understand with stream power is that changes in stream power. So if you have high stream power and then a low stream power and then a high stream power, the responses are going to dramatically change depending on what that is. So anytime there's kind of a drop in stream power, that's where you get sediment deposition, and that's where you get that energy dissipation. Compared to the stream power or the unit stream powers upstream and downstream. There are also some unit stream power thresholds that I like to look at. So if unit stream power is too high, you can start to expect that you're going to see significant widening of the stream corridor. So not just the channel, but the corridor itself, which again may be potentially hazardous depending on what's on the outsides of those. skip that. So what is an FHZ map? What is a fluvial hazard zone map? There are 6 different components in a fluvial hazard zone map. The ones that are most important to you guys are the active stream corridor and the fluvial hazard buffer. And that's what we're going to talk a little bit about today. You guys also have a geotechnical flag, which I'll kind of hit at the end as well. But for the most part, that's you know, those are really what you guys are going to be focused on, and I want to spend my time talking about those with you. So first, we're going to talk about the active stream corridor. That active stream corridor is what we were talking about before. It's kind of that floodplain floor. It's where the channel can move around, and it's where sediment deposition has happened. It's where channel erosion happens. And I want to be clear that there's a difference between channel erosion and valley margin erosion. So, you know, kind of just slow, you know, erosion of a channel bank into the floodplain versus erosion of one of the bigger sand terraces that's out on Sand Creek. And the active stream corridor is really where we expect to see most of the hazards. It's again, like it's where channel movement is expected. There's a picture of on the left there, again, of the same rain, and you can just see how it exploded and took up the entirety of the valley floor there when it had a big energy flow with a lot of sediment. And here's a zoom in of that same area. So this is the active stream corridor delineated on a pre-flood aerial with, I believe it's actually delineated with pre-flood topography as well. And this is what that looked like after the flood. And so you can see that during big flow events that you do see the river take the majority of the active stream corridor back as it's, you know, not even as its floodplain, but just as its active valley or active geomorphic floodplain, perhaps. There's another way of looking at this in urban areas, and I realized that for the most part, the Sand Creek, well, actually all of the Sand Creek study was looking at active stream corridors kind of in a less developed setting, so you could still see the topographic signatures of where that river or where Sand Creek was going to start taking space again. But they're just immediately downstream through Aurora and Commerce City. Sand Creek is highly urbanized, and there's a second way or a second protocol to develop fluvial hazard zone maps and active stream corridor in urban settings. And that protocol really looks at the potential for just channel widening because that's the primary hazard in channelized urban settings. So I just want to let you guys know that that's out there. It's not something that was done as a part of the study we're talking about today, but it was something that I did ultimately end up looking at for the reaches downstream, if that is at any point of interest to talk about. So the second component is the fluvial hazard buffer. And again, that's the area where if the channel moves into a valley terrace or one of the sand terraces or the valley margins, how far back you would expect that terrace to fail and be swept into the river. So it's really looking at areas that have never been part of the modern stream corridor, but that the river could take in the future. And so again, it's not just this historic piece that we're looking at when we're doing this mapping. We're looking at the future, and the fluvial hazard buffer is a significant part of how we're looking forward for some of these hazards. The two photos, the one that's in color is of Fish Creek in Estes Valley. And, you know, I liked when I look at that creek, it blows my mind. That creek, you know, typically only has a half a CFS in it, you know, most of the time, if anything, but it just goes to show how much energy can come down some of these systems. And the watershed size on that is only about 3 square miles, but it just goes to show how much energy can pulse down these and how much destruction can come out. during a major flood event. The black and white photo, I think, is Monument Creek, and I think that was in 1935. So again, something we've been dealing with for a long time, and now we finally have a planning tool that allows us to look at that. And this photo is East Plum Creek in 1965. So you can really see the valley margin erosion in this one. Again, the river is taking space that it had never occupied before when you look at this photo. And this is a creek that's in a fairly similar flow and climatic regime as Sand Creek. So this is what we're expecting when Sand Creek floods. So beyond kind of that, that erosion into the hillside or erosion into the terraces that we're talking about with the FHB, the streams in the Colorado Piedmont, like Sand Creek, have this other hazard associated with them. And that is that in a major flood event, the entirety of the active stream corridor can flip over or can move. So it's not channel movement within the active stream corridor. It is literally that the active stream corridor can shift location in its entirety. And that's what you're seeing with these photos here. So this, again, is East Plum Creek in 1960, before and after the 1965 flood. And the seafoam green and the lighter blue are both pre-65, and then the darker blues are after. And you can see that the whole thing almost just flipped over. And so when you're looking at the Sand Creek, when you're looking at the Sand Creek mapping and you're seeing this big fluvial hazard buffer on it, it is to capture this hazard, it's to capture the potential for this type of response of the active stream corridor to happen. Looking specifically at Sand Creek, what does this mean? So when we look at the active stream corridor, which is the yellow, we're looking up at that blue house on the right. So we're looking at, again, channel movement, bank erosion, floodplain inundation, deposition, potentially small channel avulsions, which is just change of the channel location in the floodplain. And we expect to see damage like this, and in addition to the inundation damage that happens just due to water. But when we're looking at the fluvial hazard buffer, which is the red, we're expecting to see damage like the green townhomes down on the lower left. So we were expecting just the ground to come out from underneath of it and the facility or the building to collapse as the ground underneath of it is swept away. So I said there was one more thing I wanted to chat about, and that was the geotechnical flag. So there's one geotechnical flag on Sand Creek, or it's actually on Coal Creek because it's upstream of E470. And a geotechnical flag is an area where, just due to the erodibility and the steepness of the slopes and the consistent steepness of the slopes, it is possible that erosion could extend beyond the boundary of the fluvial hazard zone buffer, or the fluvial, fluvial hazard buffer, beyond the FHB, sorry. And that one location is kind of towards the upstream into the study area near Jewel, just downstream of Jewel. There's already a ton of gullying that's happening there. What I think has happened over time is the channel was moved and it's been incising, and the hillsides on the eastern side are adjusting to the fact that the channel is moving down. So it's highly, highly unstable on those big right angle bends on the east and northern sides of the creek in there. And so as a result, that got marked as a geotechnical flag. So a little bit about use, obviously hazard reduction. And I really hope that these can be used for site delineations, site development and planning review, trying to get, as many assets and as many people out of these super hazardous areas as we can. And again, like I said, if we're looking at these as opportunity areas or as green infrastructure too, this could end up with a reduction on the reliance of channelization, levees, and bank armoring. If we're incorporating these into long-term flood management plans and you know, public works and civil planning for flood control. We can also use these for assessing resilient infrastructure. So really looking at what critical facilities are within the FHB or FHZ and avoiding putting new or replacements, sewer lines or water lines into these areas that are susceptible to major channel change. Like I said, the other side of this is that there's applications for conservation preservation in terms of environmental quality, water quality, habitat, wildlife viewing, wildlife habitat, both riparian and avian, and even some upland species. And there are also great opportunities of conserved for recreational corridors. And then I kept this one in because I think it's worth mentioning, maybe not for the City of Aurora, but just kind of keep it in your back pocket in the event that you find yourself in a situation. But these are also really useful for wildfire because wildfire changes the sediment and water balance of a watershed. And that's not something, again, that traditional hydraulic modeling really deals with, but FHZ mapping can. So just stick that in your pocket. Maybe in 5 years, it'll be applicable to you in some way or another. But I wanted to leave that in there. And then a couple things about communication. And this is coming from my experience talking about this for, like 6-7 years now. And these are the key things I like to hammer on. The fluvial hazards exist whether they are mapped or not. The lines on the map do not change whether they are on the ground. They are there. Areas are hazardous, and this is a way to communicate the risk to people making decisions and to people who are living in the areas. It's not introducing any risk to a community. The risk is there, the hazard is there. And additionally, I really like to frame this in the realm of just being able to provide additional complementary information to FEMA floodplain maps. This is not intended to replace them. It's intended to be kind of the left hand to the right hand or the right hand to the left hand. The best decisions are made with both in terms of flood hazard and flood risk planning in a watershed. We've developed a bunch of resources as a part of my work with the Colorado Water Conservation Board. They're on the website under the resources tab. Again, if you're, 5 months from now, if you need a refresher and you don't want to call, quick start guide, some work on easements, overlay district. And then additionally, we have work up there. It's Appendix A of the technical protocol that reviews at the time, so 2018, 2019, every program in the United States that was attempting to do something like this at a municipal or a county level. So if you're interested in precedents, there's a whole document on that as well. And with that, I'm ready to answer some questions. And again, thank you for your time. And I look forward to talking to you in person. Thank you.